Hello, my name is Miro and we will continue with the Renewable Energy Technology course, now with a lecture on geothermal energy. There are only three parts of this lecture. First we will talk about the origin of geothermal resources, then we will shortly look about the environmental impact, exploitation methods, and finally the most interesting part, electricity production from geothermal resources. The goal is to have a very compact and quick lecture focusing only on the major issues. You are recommended to read additional sources if you need to look at the deeper details. First and foremost, we don't know much about our planet, but what we know, deducting from some physical features and signals that are given to us from the crust of the Earth, is that it's actually composed of a hot interior, a molten core inside the globe, which is pretty hot. How hot it is, definitely it's impossible to go there and measure it, but it is believed that the temperature inside the core is several thousand degrees, pretty much close to what the sun would offer. The Earth, the composition of the Earth, as far as we know it, is certainly composed of different layers. Reaching towards the outer surface, they become solid. And where we are and where we can reach with drilling and exploration, it's actually a very, very short layer of the very, very outer part of the crust or the lithosphere. And we can easily feel that the deeper we reach, the hotter the Earth becomes. The asthenosphere is the half-molten liquid part on which the continents or the tectonic plates reside. And the origin really of all this heat is a bit uncertain, but what we definitely know is that maybe already at the beginning of everything, more than 4.5 billion years ago when the planet was created, the gravitational forces and the whole process of creation of a solid body actually generated heat at the core, in the center of the globe. Then the Earth started to cool down. It was certainly much more active, much more hot in the very beginning, much warmer inside. We live now supposedly in the middle of the life cycle of this planet and the entire solar system as a stellar system. So it also is valid for our planet that is definitely somewhere in the mid-cycle of its cooling down process. However, if the major heat was coming from the creation of the planet, it should have cooled down for several 100 million years. This is a comparatively short time in geological terms. The reason for the Earth still being pretty hot inside is actually some sort of a decay, gradual slow decay of radioactive elements, certain isotopes that we know about, which exist everywhere on the planet, definitely inside it, and not only there, but also in the solid crust of the Earth. Maybe also some chemical reactions are involved. What happens at the upper edge of the planet, where we actually exist, and where the solid bodies of the lithosphere, the solid parts of the crust, are situated, is that the entire perimeter of the planet is composed of actually quite movable plates. We call them tectonic plates, and this is where the continents reside. The entire land mass is in motion. A bit difficult to comprehend, especially for the human brain. This dimension is very, very difficult actually to imagine, but there are pretty good signals shown to us how the continents are moving. And it's not only the continents, but this also involves the bottom of the oceans. The best visible features are the fact that the African continent is pushing towards Europe. And this is what actually creates the trench here under the Mediterranean Sea and the mountains all around southern Europe, including the volcanic territories of Italy, Greece, the Greek islands, and the Azores Islands in the Atlantic. The other very noticeable part is the Pacific plate, very actually quickly moving towards the northwest, and pushing under the Asian plate, creating the deep trenches where the most dramatic ocean depths are noticed under the Asian plate, with a whole range, a whole string of volcanoes as a result. The same happens on the west side of the American continent, from north to south. The reason for all these movements is the fact that inside the Earth's core and towards the outer perimeter, the molten elements, or the molten rocks simply, are convecting upwards, then subsiding down, and thus creating some kind of a force that pulls the continents in a certain direction. The different continents move with different speeds. It's a bit difficult to measure, but actually it is possible to measure, especially now, these days, with the modern digital tools that we have. And on average, we can say that the tectonic plates are moving with a few centimeters per year, approximately the speed of fingernails growing. The most dramatic scenes, again, are the fact that the American continent and the African plate are pulling apart. At the same time, in other places, certain plates are pushing down under others, or definitely towards others. For example, the Indian subcontinent forcing itself towards Asia and creating the Himalaya mountains. A spreading center, or a place where two plates are pulling apart, would be the typical ridge, for example, the Mid-Atlantic ridge. The two plates digress, and at the same time create a space for young, comparatively geologically, in geological terms, magma to come up on the Earth, create actually new crust in a way that it fills up the space and then bulges upwards, being a very active volcanic center. Perfect example, Iceland and all the islands along the Mid-Atlantic ridge. At other parts where one tectonic plate would be actually subsiding or beneath another one, we call a subduction zone. And there, one of the plate actually goes deeper, melts, and creates a bit further inland for the plate that stays above, very active volcanic area, mountains, and so on. This is a similar explanation of how these processes are going on. Typical example for the spreading center, or the ocean ridges, with its own rift zones or fractures, if there is certain relative motion in a different direction for the plates, and the subduction zone of one plate beneath another, creating a volcanic range. Or a rift valley created by two or one solid continent plate being torn apart. Best example is the rift valley in Africa. The African Horn is being separated from the rest of the African continent. And this again creates an active string of volcanoes. These are exactly the places or the areas on Earth where we can easily reach its hot interior, or where the hot interior presents or manifests itself to us by easily reachable hot territories or hot areas under the surface. And these are exactly the places where these noticeable events as a result of the tectonic motion are being noticed. The trenches, subduction zones all around the Pacific Ocean, the Mid-Atlantic ridge, and again the pressure zones between Africa, Europe, the Rift Valley in Africa, and the northern part of the Indian Peninsula. In any place on the planet, if we start measuring the growth of temperature with depth, we can actually come up with different results. On a global average, this would be approximately 20-30 degrees Celsius per 1 kilometer of depth. It's not much, And in solid, old in geological terms areas, like for example the Scandinavian peninsula, this is pretty low, approximately 10 degrees per kilometer. On good geological sites, the geothermal resource, we assume it as good, economically harnessable, would be between 30 to 60 degrees per kilometer. So we need to drill definitely a couple of kilometers to reach some sort of high temperature. In very active areas, of course, we can have temperature gradients of the sort of 100 or even more degrees per kilometer of depth. And this is one example here of the different temperature gradients in different typical zones around the Earth's crust. This is one example of measurements being made, actually pretty theoretical estimates, beneath Europe, what's going on a very, very deep level. We actually cannot easily reach to that level. This is more or less the limit of any economical drilling. But at the shallow places, it is comparatively easy to reach to hot enough zones where the temperature can be utilized economically. This is the way we imagine the most possible or the most feasible option for utilization of heat from the Earth's interior. Basically, we rely on water. This is rainwater mainly, precipitating somewhere and then seeping through the Earth's crust deep down, reaching the warm zones, and then in some way coming back to the surface. We will talk about this in the next section. As a summary, the thermal life of the actual geothermal source beneath the Earth's crust is pretty much similar to the lifetime of our star. So for our own perspectives as humans, this is a renewable resource. It will sustain much longer than any foreseeable or comprehensible for us timeline. It will definitely also be depleted in the very, very long term when the stellar system actually reaches the end of its life or when the Earth finally cools down. It is believed that the slow decay of radioactive isotopes at this moment actually, well, in our lifespan, is what supports the continued hot interior or high temperature, very high temperature in the Earth's core. That temperature doesn't really reach us because the crust of the Earth is a very good insulating material. It is difficult for us to reach down and actually get to those hot territories. And we rely on certain the movement of tectonic plates, and exactly on the boundaries of those tectonic plates that the hot interior comes slightly closer to the surface so we can actually reach it easier.